solving of Coulomb's law and superposition of forces and electrostatic forces and vectors associated with these forces. So the electric force between charged particles at rest, sometimes we refer to that as electrostatic force or as Coulomb's force, is like all forces and behaves in the same way as we have learned in Newton's second law when we use net forces is equivalent to mass times acceleration. It has both magnitude and direction because it's a vector, and the net force acting on a certain object is always the sum of all the forces acting on it. That's why we can write down the equation for the net forces on a certain object with summing up all the forces that are acting on it. This is the principle of superposition of forces. We call this as superposition of forces. And we have learned similar stuff in Physics 1 in chapters 4 when we were talking 4 and 5 when we were talking about forces. So we use the rules of adding vectors to obtain the net force on an object by adding different vector forces acting on it. So it may be a good idea to review addition of forces in chapter 4 and chapter 5 of your Giat Colley textbook. So going through that vector addition review will be really beneficial. So what if you look at these two vectors? We had discussed this in chapter 3 also. So there is a force vector F1 and F2. The different ways that we can add the two vectors is by using the tip-to-tail method. If we pick up this vector and use it as a base, so then we drop this vector in the same direction parallel to its actual original direction and drop it over here. So we can see that F2 is this way. And then we join the tip-to-tail method technique and find the resultant force at shown by F vector is equivalent to F1 plus F2 vector. So the total force or net force is given by sum of the two forces. And the other method is the parallelogram law of vector addition. You can complete the diagram by drawing parallel sides to the parallelogram, and the diagonal represents the sum of the forces. The other way is the analytical way, where you find the components of these vectors. So if you just take this original vector and have the x and y axis drawn, so F1 is this way, and this is the one that we use a lot. This is positive y-axis, this is negative y-axis, this is x, and this is minus x. And the other vector seems to be pointing this way. So we break this into their respective components. So F1 will have its two components. One is F1x, which will point this way, and then it will have F1y, which will also point this way, F1y. So that's also parallelogram law of vector addition. And from trig, we know that F1x will be equivalent to F1 cosine of theta, and F1y will be F1 sine of theta. So it's kind of a review for vectors. In the same way, we can have this vector also resolved analytically. So we know that this one has its y component and x component as well. Its x component, maybe we put a different color for this one. And so we have our vector F2. So F2x is this way, and F2y is in the downward direction. So you can find the F2x components as well. F2x will be F2 cosine of theta. Definitely the angle here is going to be different, so maybe we can put theta prime, or maybe we can use theta 1, which is a better idea, and theta 2 for this one. And in the same way, we will have F2y, which is equivalent to F2 sine of theta 2. So this is how the vectors are resolved, and this is the graphical representation of vectors, and this is the analytical way we solve them. And then we sum up all the x components together, and we kind of, if for a vector like this, if it's resolved like this, we can make a grid like this, and we can say forces on this side, and we say x direction or horizontal direction forces and y direction forces. So all the y components can be written here. So f1, we can write f1x, which is f1 cosine of theta 1, and you can write f1y, which is f1 sine of theta 1. You can go ahead, whenever a problem is given, you might be given forces, you might be given angles, and you can go ahead and find out the components here. And in the same way, we can resolve f2 we can find the values. f2x is f2 cosine of theta 2, and f2y is going to be f2 sine of theta 2. So you will get the vector values if I give you the value for f1, if f2 is given and theta 1 and theta 2 are given, you can find the net force by finding the components first. You'll find fx component, which is the sum of these two components, and then you can find fy component, which is the sum of these two components. So the actual fnet vector will be then fx, whatever value you get, I cap plus fy j cap. So whatever value is obtained here, and then you can find the direction of the vector. The direction of vector is always found by tangent of theta, where it is going to be the y component of the vector over the x component of the resultant vector that you found. And if you are going to find the magnitude of the net force, then you know that you're going to square root the x component and the y component square. So this is a general way of resolving vectors analytically, and we have definitely learned this in previous classes. And incidentally, if the vector is in the downward direction, you should expect a negative value for this one. And all vectors in the positive direction, this will be a positive value, this will be a positive value. f1y will be a positive value because it's in the upward direction, but f2y will be negative because it's in the downward direction. So the angle will determine that itself. So it's a good idea to work on one of the examples where three vectors were lined up. We have three charges in a line. Now Q1 is exerting force on Q2, Q2 is exerting force on Q3, and they are all exerting forces on each other. But they are organized in a line, and the values of the vectors are given to you. So we have Q1, Q2, Q3, and now we are going to determine, calculate the net electrostatic force on particle 3, which is Q3, due to the two other charges. So we will use the superposition principle, where the net force on particle 3 is going to be the vector sum of force F31 vector. F31 is the force exerted by particle 3 on 1, and F32 vector, force exerted on 3 by 2. Or you could, in some textbooks, they also write this as F13, force exerted by 1 on 3. So maybe we'll use that terminology because it's easier to understand it that way. Force exerted by the net force that 3 is experiencing is the vector sum of forces exerted by 1 on 3 and force exerted by 2 on 3. This is easier way of writing it. So the overall net force will be F13 vector plus F23 vector. Before going ahead and solving this, we need to find the magnitude of the vector F13 and F23. So we will go ahead and apply Coulomb's law. So Coulomb's law will give us the magnitude of F13 is applied to find magnitude of F13 and magnitude of F23. And magnitude of F23. So applying Newton's Coulomb's law, F13 vector magnitude will be k times magnitude of Q1, magnitude of Q3, maybe we can keep it as bold because the given quantity is bold, Q1 and Q3, whole divided by the distance of separation between 1 and 3. So squaring that, go ahead and substitute the values. K will be 9.0 cross 10 to the power of 9 Newton meter square divided by Coulomb square, and your Q1 magnitude is 4.0 cross 10 to the power of minus 6 coulombs. Do not forget the micro. Sometimes we miss putting that, 10 raised by minus 6 coulombs, whole divided by the distance of separation, which is 0.50 meters whole square. So once you go ahead and solve this, your F31, your F13, which is also equivalent to F31 due to the equal and opposite Newton's third law, that force exerted by 3 on 1, and the magnitude of force exerted by 3 on 1 is the same as magnitude of force exerted by 1 on 3, but there are equal and opposite directions. It's a repulsive force between 1 and 3 if you look at their directions. So that value is given by magnitude 1.2 newtons. We will resolve the issue of directions later. Let's first get the magnitude. In the same way, we will find out F23, which is the force exerted by 2 on 3, will be K times magnitude of Q2, magnitude of Q3, whole divided by the distance of separation between 2 and 3, and square it. Go ahead and substitute the values again to get 9.0 10 to the power of 9 Newton meter square over Coulomb square. It's a good idea also to pause the video here and go ahead and solve these yourselves and then cross-check the math work. Minus 6 coulombs and then multiplied by 3, which is 3.0 10 to the power of minus 6 coulombs. And then go ahead and divide the distance of separation is given between them, which is 0.20. And in this case, it was 0.50 because you are adding the two distances of separation. So it's 0.20 meters whole square. So plug in the numbers in your calculator and go ahead and solve it. The value that you should get for F23 is going to be 2.7 newtons. Now I have both these. Now we need to determine what direction. Since we were calculating the magnitudes of forces, we omitted the signs of the charges, but we must be aware of them to get the direction of each force. So now if we look at this direction of forces, the force exerted by 2 on 3 is attractive. If it is positive, 1 is negative. So which direction will 2 and 3, which direction will 2 exert a force on 3? That is towards. So is it right to say that F23 will act in this direction? Because at the location of charge 3, the direction of the force will be pointing towards charge 2, right? And because the force of repulsion between Q1 and Q3 is in the opposite direction, so and it's farther off from there, that's why the direction of the force between 1 and 3 will be in the opposite direction. So it will point this way because it's repulsive. So that's why you write F13 as the direction of the force for this one. So now that we have the directions ready, and it's a shorter vector because it's farther, F23 is a longer vector because it's closer. So the magnitude of the force is going to be greater. If you can see the numbers as well, F13 is 1.2 newtons and F23 is 2.7 newtons. Similarly, F32 would also be 2.7 newtons in magnitude, but the direction would be different. So we go ahead and show the diagram is shown over here, like how the vectors are representing, and then we go ahead and find the net force. So in order to find out the net force, now it's a vector. The net force will be, we have to use the appropriate signs. So F23 is negative, so we will have to write minus 2.7 n because it's pointing in the negative x direction, and F13 is pointing in the positive direction, so 1.2 newtons of F13 will be in the positive direction, hence giving us a net force in the negative direction, which means it's acting in a negative direction. So this is a vector, so directions are important. We are no longer writing this as magnitude. The magnitude of the net force can be said to be 1.5 newtons, pointing to the left. So this is how these superposition of forces, force problems can be worked on. Moving on to a more complex problem where we have the charges are not lined up in one direction, like in a straight line, but instead they give a formation of a triangle. So for example, we have charge 1 is over here, charge 2 is at this location, and charge 3 is at this location. In order to understand the direction of forces, it's very important to understand this vector diagram. There's a distance of separation between the two is given as 60 centimeters, 52 centimeters, 30 centimeters. So we have already given all the values, but we need to work on the vectors, the direction of the forces, and the net force experienced by charge Q3, if that is what we are trying to find out. So this is a multiple charges over here, and we can go ahead and find out the various directions. So in order to understand, the distance of separation between Q2 and Q3 is very less. So if you look at it, it's in line, and hence the direction of force, they are both positive. There will be a repulsive force. You can also use the F32. F23 is the force exerted by 2 on 3. And I like to use the terminology F23 instead of F32, where F23 means force exerted by 2 on 3, while your textbook does it other way around. It does 3-2, which means force experienced by 3 due to 2. So it really doesn't matter as long as you keep the terminology okay. The magnitude of F23 and F32 will still be same. It's just the directions for direction purpose. So if F23 is going to be the force exerted by 3 on 2, and it is in a direction opposite because of the repulsion. So that's why you see this longer, taller vector shown over here. In the same way, we have F13 or F31 is the force exerted by 1 on 3, but because this is negative charge and this is a positive charge, so it's going to be attractive. So the direction of the force vector will be this way. The best thing to do with this is to actually resolve it into vector components. So we go ahead and find the vector components for these. So if we have this diagram over here, we kind of first find the vector for F13 and F32. So we have F32 or F23 this way, since I use F23 terminology as the force exerted by 2 on 3. And then because it does not have any x component, it's directly lined in the y direction. So that is the direction of F23, the force exerted by 2 on 3, or you can also write it as F32 if you want to remember force exerted on 3 by 2, or you can remember the terminology force exerted by 2 on 3. It really doesn't matter. The magnitude of the force will not change. So then we have another vector which is actually F31, but it's directed this way. And it's a smaller vector because it's farther away from our number 3. So we call it F13, and we can resolve it into vectors in respective directions. F13x is this way, and F13y is this way. So if we do the parallelogram law of vector addition, we know this is theta. The angle here is 30 degrees. As it is, this is 90, and the 30 degrees is given over here. It's the same angle. If we draw, it's the vertically opposite angle, so this will be 30 degrees over here. So I hope you understand. We are drawing the vector over here. This is 30 degrees over here. So if we extend the line here, this also is going to be 30 degrees. So that's exactly what we are doing here. So we know this is 30 degrees. And then we go ahead and find out the resultant vector. I would suggest making a grid here as well. This really helps organize the work. So you write down forces here. You write x direction forces, and you write down y direction forces. So this helps us segregate the components very easily. And so we can put F23, the force exerted by 2 on 3. So it will be F23x, which is F23 cosine of theta. Well, there is no x component. Theta is 90 degrees for the 2, 3, because this is 90, so it will be 0. So at least we can see why the components are 0 and all. And then we go ahead and find out F23y, which will be F23 sine of 90 degrees, because it's directly above. So that's going to be simply equivalent to F23. Okay. So once we find out the magnitude of F23, you can put in the values here. In the same way, we can go ahead and resolve the components for F13. So there will be F13x, which will be F13 cosine of theta. And you know this is theta is 30 degrees. And then same way you work on F13y, which will be F13 sine of theta, which is 30 degrees for this case. So before filling in this grid, we need to find the magnitude of the forces, and that's what we are going to do. So let's go ahead and find out F13 vector magnitude. F13 vector is the force experienced by 3 due to 1, which will be k times magnitude of Q3, magnitude of Q1, whole divided by distance of separation between 1 and 3. And your F23 is the force exerted by 2 on 3. Sorry, this is a magnitude. We don't want to put vectors over here. So it's k times magnitude of Q2, magnitude of Q3, divided by the distance of separation between 2 and 3 and whole square. So we are applying Coulomb's law here. Now we'll go ahead and substitute the values for the charges that are given to us for Q1, Q2, Q3, and the respective distances in centimeters that are given. So we will have to convert these distances into meters. 60 centimeters can be written as 0.60, 52 centimeters as 0.52, and 30 centimeters as 0.3s. So going ahead and finding one F13 where Qk is 9 cross 10 to the power of actually 9.0. So be very careful. 10 to the power of 9. I'm omitting the units because I'm going to write everything in the SI units. And the charge on Q3 is 6.5 cross 10 to the power of minus 6 coulombs because it's micro. And number 1, charge 1 is 8.6 cross 10 to the power of minus 5 coulombs, whole divided by the distance of separation, which was actually 60 centimeters, and now we are going to write it in the meters, and that comes out to be equivalent to, if you solve this should be in 2 sig figs as 140 newtons magnitude. F13 is given as 140 newtons. By the way, F13 is also equivalent to F31 in magnitude, but the directions you have to be very careful with. So in the same way, we go ahead and plug in the values for K and respective charges for 2 and 3. So 2 is 6.5 cross 10 to the power of minus 6, and 3 is 5.0. So this is your Q3, and this is your Q3, and this is Q1, and this is your K value, and Q2. So we are putting Q2 here. The order is little messed up. So, but Q2 is 5.0 cross 10 to the power of minus. Okay, so we are writing them as 65 microcoulombs, so not 6.5. 65 microcoulombs, or 6.5 cross 10 raised power minus 6. So 10 raised power minus 6 is fine, and it's 86 microcoulombs. And let's take a look at the numbers again. 86, 50 microcoulombs, and we'll go ahead and write this as 65. So you'll calculate using the not 10 to the power of 5, but you can use 65. And the other one is 50 microcoulombs. So whole divided by distance of separation is 0.30 whole square. Okay, so once you solve this, you should end up getting 325 newtons for this F23 magnitude, because it's closer. So as it is closer, that's why we are going to get a larger number for this. The next step is to find the net force. So before finding the net force, we are going to find the components. Your F13, now that we have the magnitude, since the grid here has no space, so we can go ahead and find F23 is going to be exactly same because it's 90 degrees. So whatever value you found for F23 is 325 newtons. By the way, this is 0 newtons for F23x. All we have to go ahead and solve is F13 and Y and F13x. F13x is simply 120 newtons. If you go ahead and divide it by 2, because in the Y direction, cosine of 30. So F13 is 140. Cosine of dividing it by cosine of 30 gives us 20. So this comes out to be 120 newtons. And once you put in 140 here and sine of 30 degree here, so you should end up getting 140 divided by 2, so close to 70 degrees. But since it's in the downward direction, make sure you put this as as a negative value, because F13y is in the downward direction. Do not forget the negative sign. And then you can find the net x forces just by looking at this grid. Net forces in the x direction will be sum of this and this, that is F23x and F13x, and that is just 120 newtons. And the net forces in the y direction is going to be the sum of 325 and subtracting it with minus 70, these two, and we end up getting 225 newtons. So now we have the components of the resultant vector. Then we go ahead and see our F net as a whole is Fx component vector plus Fy, which is the sum of the x and y components, and we go ahead and we can also write it as vectorially, like 120 I cap plus 255 j cap, where I and j are unit vectors in x and y directions. This is how we represent a vector. And if we try to look at it, looks like it's in the positive direction, 120 units this way and 225 units a bit longer this way. So this is our I vector and this is our j vector, and the resultant of this, if we do the parallelogram law of vector addition, this is going to be the F net vector. Okay, and we can find the magnitude of the F net by simply taking the square root of the x component and y component, squares of the components, and the square. So if you substitute 120 square and 225 square, you should end up getting the magnitude of the net force as 280 newtons, which is this vector over here, which is the diagonal vector that you see is the magnitude of the net forces, and it is 280 newtons. If you want to find the direction of this, then we can go ahead and find the direction of the vector. That means this angle theta of the final vector. The direction will be given by tangent of theta is equivalent to Fy over Fx. Then you take the inverse tan and you end up getting Fy over Fx. Go ahead and plug in the values and find out what you're getting for the angle. So theta, which is the final angle, comes out to be 65 degrees. Make sure your calculators are in degree mode. So it's this final angle of the superimposed forces, which is in the positive x direction and positive y direction. This represents your Fx net, this is your Fy net, and this is the overall magnitude of the vector that we found. So this is how we solve these problems. One problem I have from your textbook, which is problem number 12 from G.N. Colley textbook, and let's get started by working on this one now that we know how to solve problems using vector superposition of forces. So we are applying the same technique here. So there are three charges which are equal in magnitude, and we want to find out the magnitude and direction of the net force on each particle due to the other two. So it's actually a long problem, but we'll work on this one. So actually, because their distances are same, it's like an equilateral triangle. If we find for one, we can go ahead and find for others as well. So the forces on each charge lie along a line. So if you see this charge is exerting force on this charge is exerting force on this charge is exerting force on this charge, and this charge is exerting force on this charge. Same goes for this one as well. But if we find the force exerted by one on the other, it's going to be the same force exerted by the others on each other, because they are same and at equal distances from each other. So let's assume that d is the distance of separation between them, and we name this as q1. Let's name this charge as q1, this one as q2, and this one as q3. This will help us organize the work. So let's say force exerted by 2 on 1. So we'll say force exerted by 2 on 1 is k times q1 magnitude, q2 magnitude, divided by the distance of separation between the two, which is an equilateral thing, so we'll write d square. Even You could put this as magnitude, but we know they are positive charges. So the magnitude F21, if you go ahead and see, is K times Q1 and Q2 are same. So we could ideally write Q square over D square, right? So the angle for an equilateral triangle, we know that it's going to be same. So let's go ahead and find out the values for these. Since F21 is KQ square over D square, and then we can go ahead and find F31, which is the force exerted by 3 on 1. So let's go ahead and find these two forces exerting force on this one. So that's going to be K times magnitude of Q1, magnitude of Q3 divided by D square. If you notice something, since they are equilateral, they are all equal, there are equal distances, the charges are same, so it will be Q square over D square again. We will not solve their values yet, but we'll go ahead and see. I will leave you to solve these yourselves, plug in the values and find the F21. You have 17 microcoulombs and you have the distance of separation as 0.15 meters. Here, this is 17.0 cross 10 to the power of minus 6 coulombs. Go ahead and attempt this and plug in the values. Pause the video here. I'm going to just show you the method. Let's make a x, y axes here, y prime, x prime, and x. Let's see what happens to the direction of the forces. The force exerted by 2 on 1 is pointing this way, and the force exerted by 3 on 1 is exerted this way. So we have each one of them is now getting split into their respective components as F1x and F12, F12x or F21x and F31x and F31y. So let's see what happens. So we will have the force, this is your F21 because it's directed this way. So F21 is directed this way, and F31, force exerted by 3 on 1, is directed this way. So it will have F21x component here, and the y component is shared by both of them. F21y will be this way. And similarly, we will have F31x this way, but F31y will be in the upward direction. You can do the parallelogram law of vector addition. They will actually be at a similar angle because this is going to be 60 degrees. So this is your F31. This angle, they are all 60 degrees, being an equilateral triangle, if you see that. Okay. So if we work on the grid again, or let me use another page. So if you do the grid again, the forces, x direction forces, and the y direction forces. So you do F1, F21, and you do F31, okay? And then you have F21x, which will be F21 cosine of theta. You could put theta 1 or theta 2, but theta is same for all of them. And then you do F21y, which will be F21 sine of theta. In the same way, you will do F31x, which will be F31 cosine of theta. Theta is 60 degrees because it's an equilateral triangle. So, but remember F31, which direction is F31? If you are measuring it from the positive x-axis, so it's a minus here. So make sure you put a minus here. And then we have F31y, which is actually in the upward direction. So no problem about that. It's going to be F31 sine of theta. Apparently, the magnitude of F21x and F31x is going to be same. if you find the sum of them, it's going to be actually 0, because one is positive, one is negative. If you find out the magnitude of F21 and the magnitude of F31, you will find that they are coming out to be equal. So the net forces in the x direction will actually be 0. You will have only contribution from the y direction of forces. So I want you to solve this fx, complete x, and find out what value you're getting here, the net forces. And then if you see that this F21 must be equal to F31, and the net forces in the y direction will actually double up because they are both in the upward direction. So this will be doubled up. They are both same. And so you'll get 2 times whatever is obtained here. So I'm giving you this problem to solve. So you'll see the forces will, net force will actually double up. So work on this one, and so in the end, the force that you are going to see will be actually 2.00 cross 10 to the power of 7, 2 newtons will be the magnitude of the force. So the direction of F1 in y direction is the both the forces will be in the y direction. When they double up, the resultant force will be in the y direction only, because the x components are one is plus, one is minus, and the resultant effect is going to be in this direction, while as the forces in this side cancel out. So that's why the forces double up. And also notice that the x components are bisecting the opposite sides of a triangle, thus the force on the lower left charge is cancelling with the negative side that I already told you. Finally, the force on lower right charge is also the same magnitude and will point in the 30 below the x-axis. So if this is 30, this is 30, and your magnitude of forces here, because this was actually 60 for the equilateral triangle. So I would suggest plugging in the numbers for these forces and finding out what is the magnitude A. You will first find the magnitude of the force, and then go ahead and find the magnitude of the find the angle, although the angle will be 90 degrees, because the forces in this and this direction are going to cancel out. So this is an assignment for you to complete.